Okay, let's have a class and then we will go over the exam one and I'll return to you. Then I will talk about some questions. So today's class we want to talk about some chemical reaction with amino acids. With amino acids. There is a lot, and we just pick some related to the food processing. So the first thing, everybody knows how we gonna testing free amino acids in a solution or in the food products. How do we know there is a free amino acids there? This is the one we could be working with, let's say, products, working with a chemical called hydrogen. So the hydrogen structure is a 6 carbon and a 5 carbon, and this is have a double bonds, the carbonyl group with hydroxy bonds right here, like that, okay? If they reacted with amino acids, and we know amino acids looks like this, amino group or side chain, a proton and a carboxy group. If this is reacted, what will happen? Obviously, you will generate ammonia. You will generate carbon dioxide. You will generate those aldehyde. But those are not very important. The important chemical is right here. It is actually is 900 hydrogen. 2 of them will be connected together. Okay, so at the middle will be a nitrogen, and then you go here, and then you can draw like this, like that. Go this way, goes that way, and then so what is this one called? Hydrogen dentin. Now, why I use this color? The reason is we could be measure the absorption of the spectrometer set at wavelengths 570. For most of them, alpha amino acids at the color spectrometer at 570, it will be showing you a purple color. Therefore, we know there is a free amino acids. And this purple color, we also call it Lohmann's purple color. However, we have to be careful. There is one exception. What's the exception? Is chlorine or hydroxychlorine. This is exception. For them, it is A absorption at 540. It will turn yellowish color instead of the brownish color. So that's different. Now why? We know that the structure is different. Because chlorine is like a ring. So we know about these. It's 3CH2, it's circle. And the hydroxychlorine is you just add hydroxy bonds, right, hydroxy units right there. Okay, so this is the first one, which is 3 amino acids with 9 hydrogen will generate a product which is hydrodentin. It will be showing you a purple color. And we using the wavelengths at 570 using the spectrometer. And this is a very easy and quick test. We could see whether in a solution or in the food products we had a free amino acid existing. Okay, so this is the first thing we want to talk. Then the second thing we want to talk the reaction is called racemization. So what is the racemization? Let's say I have L amino acids. During the food processing, we were using, or as a food product is exposed to alkaline solution. At the same time, using extended heating, especially more than 200 degrees Celsius. And what will happen? The L amino acids will become D amino acids. And obviously you see, when L amino acids become D amino acids, the essential amino acid could be gone. And also the digestibility of L amino acids become D amino acids will be significantly decreased. So these are the two things we will be know. Now, why this will happen? Because the major reason is a hydroxy solution will be extracted. The proton from alpha carbon and create an intermediate products called carbonium. And this carbonium later on could become DHA, which is dihydroalanine. I want to make sure the spell is correct. So DHA is called dihydroalanine. Now don't be fooled by yourself. This DHA is not the DHA we will talk later on in the lipid section. Okay? So that's the overall reaction, what it looks like. But let's give you an example to explain. So let's say I have an amino group like this. Okay, I have a CH2. Let's add a group which is X. Okay, on the top is H and COOH. Okay, I'm gonna be using an alkaline solution. Let's just say sodium hydroxide. And then we're using 200 degrees Celsius to do the heat. So what's going to happen? At the first moment, we say this guy will be replaced with hydroxy will be took it out. So what is going to become? Will become NH2, C, CH2, X, with a carboxy group. At this moment, it will become like that. It's an intermediate product. And this product, we call it carbonyl. This is an intermediate product. The carbonyl could go different directions. They could go this direction. If in the food processing environment, somehow they met another proton compound, this proton compound will go back to this available area. However, the configuration will be switched, which means CH2X will goes up. So this is what it's going to be looks like. Will become MH2, C, H is go down, and on the top you will see CH2X. And this guy here is actually, we could be using this like that. Okay? Now all the other are the same. And we could remove that. So you see obviously, originally this is go down, this is called D amino acids, and this is goes called up, become L amino acids. And we said a couple of times, once this become L amino acids, what happened? L amino acids lose essential amino acid. So we talk about leucine, isoleucine, valine, phenylalanine, tryptophan. There is a 9 amino acids. It will be basically loose. The second, L amino acids, the digestibility significantly lower than D. It will become, this is L amino acids, and when you go down, this has become D amino acids, okay? And D amino acids will lose essential amino acid. And D amino acids, the digestibility is significantly lower than L amino acids, especially by gastric protease. Another thing is that there is some of the research people has been done showing if you are feeding 100 parts per million D amino acids to chicken, the chicken could generate neurotoxins. I don't know how they do that, because it's a chicken. Basically, you cannot see their behavior. Maybe they to testing their neurotoxin from the certain blood samples, or they just to see their behavior. But I just want to tell you, if you are feeding more than 100 parts per million D amino acids, the chicken will generate neurotoxin. So it's very interesting. Now, what happened for here if we goes down? When we goes down here, this will be further developed, become NH2, CH. This is H is gone, so we took this out. It will become CH2 and COOH. And this X will be released. Now, what is this guy? This chemical is very important. We're talking about today. This is called DHA. Dihydroalanine. What's the difference between that? What's the difference between the alanine? So we need to go back to explain this to you. NH2, CH2, COOH. That's alanine, is that right? That's alanine. If this is gone, This is actually CH3. When this is gone, what happens? This double bonds goes there. That becomes dihydroalanine. Okay? Dihydroalanine will be later on become cross-linking with different amino acids components, typically with epsilon amino acids. That means lysine. So, we want to talk about the next reaction is the cross-linking. So what is going to happen for the cross-linking? So this will be give you some of the examples. It is actually very interesting. So let's talk about is serine. So we have this comes out. CH2, SH. This is serine. Oh, sorry. This is cysteine. That's cysteine. Okay. There is a sulfide group right there. If a cysteine reacted with alkaline solution at more than 170 to 200 degrees Celsius, what will happen? From the chemistry standpoint, this guy will attack in here. Will attack the sulfide bonds. It will be attacking the methyl group CH2, and will also attacking the central alpha carbon. So they will generate what? They will be taking out all these SH bonds, because the hydroxy sulfur bond will be gone. So we'll have a DHA generate. Okay? So we'll be generate NH2, C, CH2, and COOH. That is DHA. Now, not done yet. This reaction happens, is immediately happen without generate a carbonyl. If you have a cysteine in an alkaline solution at a high temperature, they directly become a DHA. However, what will happen is that this is not a complete reaction. More or less, you have some reversible. So, for the system, the cysteines, they will have some of the residue. Once this residue happens, what will be? These two could be connected, then become what? Become a chain. So, this will become very interesting, is you have NH2, CH, CH2, COOH. You have an S generate, and then you go back, you have CH2 generate, goes C, NH2, and COOH. And then, this is a double bonds. Okay, once you connect it, this is kind of like a semi-carbonyl generate. And this could be connected to another cysteine, then become long and long. And that's called cross-linking. And this type of the cross-linking, we gave them a name called lesser-ionine. Now, this is not a big deal in the food processing. This is just an example. The cross-linking will be generated. Now, the major issue is what? Is cysteine could become a dialcysteine, will become a cysteine. So this is what happened. Is NH2, CH, COOH, CH2. You have an S here. Then you have another S here. Okay, then you go down, CH2, C, NH2, H, COOH. This is already a true cysteine cross-linking. We call it a cysteine. Now what happens is, once this cysteine generates, if in a food products you have lysine, what will be the lysine generate? Looks like NH2, C, COH, H, then go top, CH2, 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 NH2, like that. They could be cross-linked. Okay. When they cross-link, how they do? They are not just simply cross-linked. They break down at the beginning right here. Generate a carbonyl, generate a DHA. Then the DHA go back to react with this. Then generate what type of the products? It is, you need be, go down. Okay, so will be like NH2, CH, COOH, CH2, this will be 4, we just write like that. Then NH, go like this. Then go here, will be NH2, CH2, and COOH. What is the name of that products? CH. Wait a second. NH, CCOH, yes, that's correct. Okay. That's correct. What is this one called? And here we call this as a lysyl residue. What is this one called? This is called lysinoalanine. This lysinoalanine, we call it LAL. Ian, can you move this a little bit in the center? That's called LAL. This LAL seems like a little bit complicated. However, we did not recognize this LAL is widely existing in different type of the food products. So people did a research for LAL. They do microgram per gram of protein. Okay, this is equals ppm in different products. They find that in chips, this is 390 ppm. In pretzel, 500 ppm. How about milk? If the milk products is high temperature, short time heating, this is actually could be up to 1,300 ppm. How about skim milk? around 500 to 600 ppm. There is only one product has not been found any of the LAL is milk powder, evaporated milk powder. This is 0. So this is widely existing in the food products, just people doesn't realize it. This tells you, some of the nutrition scientists will tell you, milk powder, or sorry, not milk powder, skim milk, or any of the commercial milk products, you cannot do microwave heating or boiled it or long time heating, especially when you feed the baby, you want to heat a little bit up. You think you're killing the bacteria, especially like some raw milk, there's a debate about that. Once you heat it, the essential amino acids, we call it the epsilon amino acids, the lysine, is gone. And they generate a cross-link. So, that's what the cross-link happens in the food processing. Now, how are we going to do that? How are we going to prevent it? There are different ways we could prevent. One of the ways, you could be adding sodium sulfite, or you could be adding ammonia solution. They will be compete with epsilon amino acids. So will be partially to stop the cross-linking happens. Okay, so that's something we want to talk. Now, why this one is not good? Why LAL is not good? There is several things happen. Number one, we mentioned before, this is a slowly digestible and hard to digest by trypsin. Second, LAL could be existing in intestinal area. However, hard to absorb. What this mean? Maybe 90% will become urine solution, will be taken out during the urination. Number three, same we did the research. This time they are using the rats to do the research. If the rats, you are feeding 100 ppm LAL, what will happen? They will generate a kidney disease. We have a terminology called nephrosis or nephrotic toxin. Okay, so that's what will generate a kidney disease related to the LAL. Now, in our textbook, which is Introduction of Food Chemistry, they mentioned another reaction, which is they using bovine plasma albumin as an example. So the bovine plasma albumin, the major components, it is asparagine and glutamine, because asparagine and glutamine, their structure are very similar. So you can say if we drop structure, okay, CH2, we just write an N here, so we go So if this N equals 1, it is asparagine. If this N equals 2, this is glutamine. If this one reacted with lysine, and we know that what it looks like. This will be CH24, NH3 plus, NH2 plus. If they reacted, this guy in here will react. Okay, so we'll generate a cross link. They will release ammonium and generate a very long cross, which is NH2 CH. This will be go up, so that will be CH2 and go down. This will be NH, so go CH2 4, and then go down for NH2 H and COOH. They will generate this cross-linking products. Of course, this could be 1 or 2. Now, why we textbook using this as an example? This is tells you if you heat it at 115 degrees Celsius and more than 27 hours, it's just a model in the lab, and nobody gonna heat that long time. Once they heat that long time, this lysine will be gone. And this is typically happens in a textured vegetable protein. Which means the lysine in a textured vegetable protein, their biological capability will be impacted. They always have some impacts for that one. Okay, so this is an example. In our textbook, I usually write the example to explain this to you. So this is a cross-linking. So the idea here is the food products, if they have a cysteine, they have a cysteine. And we also know lysine is widely existing in lots of the food products, especially the milk products. Then, if you are using an alkaline solution at extended heating environments, they will generate a cross-linking. The cross-linking comes out from the DHA, which is dihydroalanine. Once they have a cross-linking generate, their digestibility will be significantly decreased in the body. And lots of them will become a urine solution that comes out. And also the animal study showing they may have more or less of the nephrotoxication impacts. Okay, so that's a cross-linking. Okay, the last one we want to mention is oxidizing agent for amino acids. The impact for the amino acids. So we know that during the food processing, there are some of the oxidizing reagents we will be using. For example, hydrogen peroxide. For example, this guy. Peroxyacetic acids. This is peroxyacetic acids. And by the way, we did the research with antimicrobials. If this is 33.5%, this is 5%, we combine them, then become what? We call it a sanidate. Is that right? That's what's the chemistry behind it. But the people say this is overdue. Why? Because peroxyacetic acid originally is coming from acetic acids with H2O2 reacted become peroxyacetic acids. So when we submit a manuscript, some reviewer doesn't know the products. They say, you don't need to mention about H2O2, you only need to say peroxyacetic acids, because it's originally coming from H2O2. And the company wants to make these products because they want to make it more stronger with oxidizing. And we know that it is expensive, the sanidate. That is $304 for 5-gallon pound. And also it's very corrosive. If you does not wear your gloves, your skin will be completely have a burning feeling. Okay, even will turn pale color. So that's something I want to mention. But in the food products we use that. And we also sometimes using hypochlorous acids. We call it a bleaching agent. So during the food processing, we're using those oxidizing agents. Sometimes we also more or less have some endogenous oxidizing chemical will be generated. So if you have a protein products, you have a free amino acids, then oxidizing agent are going to be working with them. Will generate oxidized products. Okay, so that's very normal. What type of thing we will be typically talk about? Methionine will be one of the example. So this is what we're going to do. Okay, methionine, what it looks like. NH2, CH2, CH2. We had an S right here and CH3. So what we're going to do? There is a multiple steps could happen. If we are using only 0.1 mole H2O2 hydrogen peroxide, this will be a target is this sulfide. So what will happen? HCOOH. These are the same, doesn't change at all. This guy will add O there, oxygen there. This is CH3. So, what is this one called? Methionine sulfur oxide. Okay, I want to make sure. Yes, sulfur oxide. Okay. Now, what you see? This could be connected with an O. Is that right? If I keep doing, I keep adding 0.1 ml, 0.1 mole H2O2. What happened? The others are the same. The other exactly the same, only this O here will have another O comes. This is called methionine sulfur form. FOME called sulfur form. They could further oxidize. If we further oxidize using another 0.1 mole H2O2, what will happen? This methyl group is not very stable. This methyl group could be gone. So will become CH2, CH2, this is S. These are the same sulfur form, and this will directly become OH. Then we're going to change the name for this. This is called hormone cystic acid. This is very typical using in a food processing. If there is a product, you have methionine, you use H2O2. What's the disadvantage for both of these two products? This is biologically unavailable. This methionine sulfur side, this could be temporary or slowly used by, we call it a gastric protease, or stomach acids, okay, or hydrolyzed by stomach acids. So you know that these are highly oxidized products. It is very difficult to use because of these very stable compounds. Great, so that's methionine, the reaction looks like. Another thing, we want to make sure it's relatively easy, okay? Cysteine, we just mentioned. I'm not going to draw everything, okay? We're going to make sure it's relatively simple, CH2 and SH. If you have a cysteine in the food products, this time you are not using that strong oxidizing reagent. Let's say I only gonna use it, which is acid. So for example, I'm gonna using just acetic acids. I think because it's a weak acid, so we're going to be using, let's say, 0.1 to 0.5%. For some reason, we're going to use it. Okay, once this happens, what will we do? This obviously will happen here. Okay, the other places will stay. What will happen? This I usually call EIO. So based on the different level, if it becomes SOH, we call it cysteine, sulfur, phenic. If it's become SO2H, we call it a cysteine, sulfur, phenic. If it's become SO3, cysteine, sulfur form. Again, these two cannot be used. And the only cysteine sulfophenic can be slowly digested. Okay? This tells us not only the oxidizing reagent, sometimes we're using the weak acids also could generate oxidizing products. Another example, obviously, is we talk about cysteine. So let's draw here. If I have NH2, we have CH2, S, CH2, H, NH2, and COOH. If this product, which is called cysteine, they are working with a weak acidic products, it will also have oxidation reaction right here. Is that right? That could be relatively weak, only one oxygen goes there. Could be 3 oxygen, and finally could become a 4 like that. So the target area is right here in the middle. Now, we will say, this oxidation reagent is not good because it will be significantly decreased the amino acids, the bioavailability. But does any examples which is good? We could give you an example, which is really good. It's for the dove. So, dove, we like its elasticity. And slightly like a collagen. And we also like its, we call it elasticity, like a collagen type of the feeling. Okay, what happened? The major components is tyrosine. So what is the tyrosine looks like? We're going to draw tyrosine like here. Okay, so tyrosine is NH2, CH, COOH, CH2, and up